Coming up on this episode of the IoT Inc. Business Show.
The technology of the software-defined product containing the digital twin is the most important technology in IoT. The most important because it's directly related to creating value. Sometimes it can be a bit confusing, so in this episode of the IoT Business Show, I share with you 3 lessons from the ICIP Technology course. The first, a simple example to demonstrate the software-defined product and digital twin. Then, an overview lesson on standards and protocols, and finally an overview lesson on IoT analytics and big data.
All this and more on this episode of the IoT Inc. Business Show. The people, the business, and the technology of the next generation internet. This is the IoT Inc. Business Show. And now, here's your host, Bruce Sinclair.
Hello and welcome to the IoT Inc. Business Show. This show is made possible by sales of my book, IoT Inc., published by McGraw-Hill, and the IoT Inc. Certified IoT Professional, or ICIP, online training and certification program. Become a certified IoT professional by completing the program's 3 courses: ICIP Technology, ICIP Business, and ICIP Strategy and Digital Transformation. Details of which can be found at www.iot-inc.com. That's www.iot-inc.com. This is Lesson 2 in Module 2 of the ICIP Technology course. A simple example of the software-defined product and its digital twin. The software-defined product is by nature highly abstract, consisting of code and data science. To bring things back to earth, let's examine a software-defined spring to reinforce the concepts learned so far. The software-defined spring will be defined at the part level. And as mentioned before, it will consist of the digital twin, which is its data and models, and its applications. Going back to our high school physics, the simple equation F equals kx represents the functionality of the spring. Apply a positive force, and there'll be elongation. Apply a negative force, and there will be compression. Although good for explaining how a spring works at a high level, in the real world, this just isn't accurate enough. It's not accurate enough because of all the other variables that come into play in the real world, in vitro. To get a more realistic picture of the spring, we need more data and more sophisticated models. What is the size of the spring? What's the gauge of the spring? What material is the spring made out of? What's the geometry of the spring? And what's its temperature and the environment that it's in? This data about the data is called metadata, and it is one of 2 types of data captured by the digital twin. Raw point data is a second form of data captured by the digital twin. It is collected by sensors, it's time-based, and it represents cause and effect. In this simple example, force and extension data is collected by sensors to get a better understanding of how the spring actually works within its environment. Again, the digital twin consists of data and models, and the data consists of metadata and raw data. The digital twin's models also consist of 2 types: meta models and stochastic and parametric models. Similar to metadata, the meta model is a model about the models. This informs the analytics on how the model operates at a high level. If, for example, gravity was involved, the meta model would capture this, so we don't have to statistically determine that we're observing gravity. If we want to start analyzing the spring, We use its raw data, but in an IoT system, that can be hundreds of thousands or even millions of points, making it impractical to compute. Therefore, we come up with a stochastic model that represents, like a proxy, the raw data points. Whereas the high-level meta model was a linear equation, our model will be a nonlinear equation, the degree of which depends on the accuracy we need. But it will not be a straight line. These stochastic models are statistical models, and they're used by analytics, whereas parametric models are designed to be executed quickly and are used by the application. A nice way to think about this is stochastic models are used to look into the past and into the future with analytics, whereas parametric models are used to look at the present with the application. To simulate even the simplest of products, a spring, it needs to be represented with a sophisticated digital twin, again consisting of two types of data and two types of models. And note that this is a digital representation of not how it looks, but what it does and how it operates. Next, we consider the application of the software-defined spring. This is the code that's used to execute the digital twins, or the models, in different situations. For example, if this was the spring in a suspension of an automobile, the application code would apply forces that would then execute on the model. Apply the force to the model, cause an effect, and get the resulting compression or elongation. Our digital twin and model are only looking at forces and compression or elongation. However, if our model took into consideration temperature and the environment, our application code could also change those variables and see what happens to the model. So together, the digital twin and the application code are a simulation of the spring in the context of the product, or in this case, the part being simulated. That's the software-defined spring. It has the model, or the digital twin, that also includes the data, plus the application. But remember, there was the trio of value. That consisted of the application, the digital twin, and the analytics. So if we were to analyze the software-defined spring, we could do it in a few different ways. In all cases, we are correlating the meta and raw data through an analyzable and executable model to look in the past by analyzing, let's say, past anomalies. What happened? By looking into the present, ensuring that the spring, for example, is operating properly in real time, and looking into the future. Perhaps we could analyze it based on past performances of similar springs to make predictions as to when the spring may crack or stop working properly. This is an example of a software-defined product at the part level. But as mentioned earlier, it can be simulated at different levels. At the part level, it's a spring. Perhaps at the product level, we would be defining a software-defined suspension. At the system level, we would be defining a software-defined car. And at the environment level, we'd be defining a smart city in which the software-defined car could operate. The simulation of even the most simple of products, like a spring, takes non-trivial computing resources in order to execute the code and the data science involved. Most IoT products will be far more complex, represented with a hierarchy of data, models, and code to achieve a realistic simulation. This is Lesson 1 in Module 5 of the ICIP Technology course, an overview of standards and protocols in IoT. It should first be noted that protocols are synonymous with standards, which are synonymous with layers, and they can be used interchangeably. While seemingly dry, understanding protocols used in the Internet of Things is strategic, because protocols are the root of standards. Standards drive networking, the software that moves the data from the edge to the core. Protocols have grown as independent silos in IoT, or more specifically, OT protocols have grown as independent silos because they've been developed individually for each of the industries they serve. Networking evolved from first SneakerNet, and that was where people would walk up to the instrumented machines, look at the displays, write it on a clipboard, and then move on to the next one. This then extended to M2M, or machine-to-machine communication, which is more like an intranet with their own proprietary protocols. This was the problem area, and this today remains the problem area for integrating IoT from sensor to cloud. There are 3 protocols, maybe 4. They are the media layer, the network layer, the application layer, and the meta layer. It's important not to conflate the protocols or layers or standards. There is more than one IoT protocol. It's important to understand each layer, their interdependence from each other, and how they all work together to deliver data, the lifeblood of every IoT product. This is Lesson 1 in Module 7 of the ICIP Technology course, an overview of IoT analytics and big data. All incremental value of an IoT product comes from transforming its data into useful information. Analytics transforms the data, and as such, is of critical importance to every IoT deployment. Analytics has been used well before IoT, but one of the biggest differences in using analytics in IoT is the size of the databases. These databases are often time series based, so by nature, this is big data. Consider the number of sensors, and they can be thought of as the columns in a spreadsheet. Then time equals 1, 2, 3, 4, they can be thought of as the rows in a spreadsheet. Depending on the fidelity of time measured, whether that's 1 per second, 1 per minute, 1 per hour, over time, these will produce very large data sets, and in fact, are the definition of big data. All this data, or big data, is stored in databases. Metaphorically, in IoT, we like to use water. So we have data streams that feed into data lakes, which are databases, and then are redirected to data pools, which are portions of databases, to be worked on by analytics. There is a direct relationship between the digital twin and analytics. In fact, the structure of the digital twin defines the structure of the analytics or the data science. The digital twin consists of 2 parts, the data and the model. The raw data comes in from sensors in a time series form and is from also external systems in an unstructured form. This raw data is analyzed by analytics for a couple purposes, one of them being to create models. Models are created to simplify the data so we can again apply more analytics in a more simplified form. It's not practical to apply analytics to millions and millions of points of data. This is why we need to create the model. Once we have created the model with data analytics, we then use data analytics on the model for further analysis. This always starts by creating the model, then improving the model, and then comparing that model with other models to provide insights. The digital twin is everything that analytics needs. It consists of a federation of data and the models. Federation means that all the data and the models do not need to be stored in one database. Instead, we point to different databases. It should also be noted that there's not going to be a single digital twin for an IoT product. There will be many different digital twins. They can be at the part, the product, the system, or in the environment level, and they can also be used to provide different forms of functionality. The structure of the digital twin is hierarchical, and as mentioned before, it defines the data science structure. This is why you always start by defining the digital twin technology-wise when designing your product. And remember, we always start with value. What's the value we need to create? What's the information we need to create that value? Then, what data do we need to create the information to create that value? And then, what technology we need to capture that data, store that data, in order to create that information to create that value. This is where the digital twin comes in. It again defines the structure for data science. A good question to ask is, well, where is the data analytics? Well, analytics is computed anywhere on the network fabric. Data is also stored anywhere on the network fabric. So the analytics can occur on the embedded system to do so-called miscomputing. It can be on the fog, so that would be in the gateways on the OT network or the IT devices such as firewalls and switches in the IT network, or it can be performed on big servers in the IoT cloud. With the exception of real-time analytics, which needs to be calculated close to the source, generally analytics is an external system. And this external system uses high-performance computing, often parallelized, to perform the heavy lifting when doing analysis that looks into the past or into the future. And this is a useful way to classify analytics: the past, the present, and the future. In the past, we ask the questions, what happened? And why did it happen? This is answered by descriptive analytics and diagnostic analytics. In the present, we ask the question, what's happening now? That's answered by rules engines and stream processing. And for the future, we ask the questions, what could happen? And what should happen? That's answered respectively by predictive analytics and prescriptive analytics, all of which we're going to be talking about next. Whether looking into the past, present, or future, the starting point for analytics is creating a model to the data. Okay, well, I hope you enjoyed that lesson. This podcast goes vertical, deep diving into different topics each week. If you prefer a more horizontal and structured approach to learning IoT business and its orbiting technologies, check out my book IoT Inc., published by McGraw-Hill, or become a certified IoT professional by completing the ICIP training and certification program. For details, just go to www.iot-inc.com. Also go to www.iot-inc.com for an analysis of this episode, links to things that were mentioned during the episode, and very importantly, the episode's PDF transcript. Just search for the name of the episode or the guest. If you're new to this podcast, subscribe. That way you'll get every week's episode delivered straight to your device. Or, if you've been listening for a while, there are 3 ways you can support the show. You can leave a rating or a review on iTunes. Just go to iot-inc.com/iTunes. It only takes 1 click to leave a rating, a little bit longer to leave a review. You can share it on social. I'm on LinkedIn, to a lesser extent on Twitter. And of course, you can support this show by buying my book, IoT Inc., or the ICIP training and certification program. It's how I pay the bills. Next week's episode is Raising the IQ of San Francisco with Pervasive Smart City Networks with Miguel Gamino. I hope you can join me then. I'm your host, Bruce Sinclair. Thank you for listening. Until next week, may your path to IoT business be a learned one.
You have been listening to the IoT Inc. Business Show.